Welcome back to CS196. So, yet another lecture of COVID-19 edition 196. Hope everything's going well. Hope online learning is treating you well. Let's go over the objectives for today. So today, the name of today's lecture is going to be Fearless Recursion, because as long as you've been keeping up with CS125, you would have been most recently you would have learned recursion. And recursion is probably one of the most scary topics that you can learn in CS125 or any introductory course. So today I wanted to take an opportunity to kind of show some visualizations for recursion, so that way when you tackle this topic, you can actually have a better understanding of recursion. So what we're going to be doing today is we are going to be demystifying recursion with some visuals. And as a result, we'll have a greater intuition of what's going on under the hood. So let's go ahead and start off with some first things first. So you already all know recursion. As long as you've taken any sort of math class before coming here to the University of Illinois, you likely already know recursion. And so here's an example of what I hope you're already all familiar with, and that's the factorial exclamation mark here. So you can see how 6 factorial, if you're not familiar with what a factorial is equal to 6 times 5 times 4 times 3 all the way down to 1. And so you might notice that in this example of factorial, you can see how 6 factorial is also equal to 6 times 5 factorial. So instead of going all the way down to 1, you can just say, well, 5 factorial is equal to 5 times 4 factorial, because 4 times 3 times 2 times 1 is in fact 4 factorial. And you can see how this kind of works in a recursive fashion. And so the recursive definition is stated here. We can say that the base case of this factorial function, this recursive function, is that the base case is 1, where once we hit the factorial of 1, that is the smallest version of this problem that we know. And every single time we make the problem smaller in size, we just want to basically, set up our function and multiply in the same way that we have here. So recursion may feel magical when you first learn it, but the fact of the matter is that it isn't. The more you're working with recursion, the more you actually see the visualizations and what's actually going on under the hood. I hope that it'll make more sense. So here is the recursive definition for factorial in code that we just saw. So if we hit the base case, which is n equals 1, we'll just say that the factorial of 1 is 1, and every single time we'll multiply, n times the smaller factorial. So if we want the factorial of 6, we'll do 6 times the factorial of 5. So how does this work? A very common issue with recursion is, you look at this function and it just seems like it works like magic. You just kind of put some things into your compiler and it'll end up just magically giving you the answer. But let's go ahead and start breaking this down. So how can we visualize recursion? Well, the first way that we're going to visualize recursion in today's lecture is through recursion trees. So here is the same exact recursive definition that we saw all throughout the lecture so far, the factorial function, and let's work on creating a recursion tree for this function. So let's say I want to find the factorial of 6. So I will just input 6 into the function. What is 6 factorial? So we'll find right up here, we have f of 6. So in order to calculate f of 6, since we're multiplying n times factorial of n minus 1, we know that in order to calculate f of 6, we need to calculate f of 5. So we're basically just going to go all the way down this recursion tree that we're building, and we'll end up hitting a base case. So what we're looking at here isn't involving any sort of data. This is all just control flow. So f of 5, in order for f of 5 to resolve, we need to know the answer to f of 4. So then we go down even further. We go to f of 4, factorial of 4. And it's the same thing here. F of 3, because f of 4 needs f of 3. And we just keep on going all the way down until we hit a base case. So we know that f of 1 is the base case for the factorial function. So what we've done so far here was just purely the control of our program. But now that we've hit a base case, we can say that f of 1 is equal to 1. So it'll return 1, and we'll start working all the way back up our recursive tree. So since factorial of 1 is 1, we can propagate upwards in our tree, and we can actually resolve f of 2 now. So we know that for factorial of 2, we can return 2 times what we now know is the factorial of 1, which is just 1. So factorial of 2 will return 2. And now that we have this answer, we can propagate further up the tree. So now, for factorial of 3, we can just simply say the factorial of 3 is equal to 3 times 2. Because now we can actually say that factorial of 2 is 2. So f of 3 returns 6. And then we keep on doing this over and over again. We propagate upwards, and then we get the answer of that function. Propagate upwards, the answer of f of 5 is 120, and so on and so forth. F of 6 is 720, and we finally completed the result that we've been trying to find. The factorial of 6, we know, is 720. And we were able to do this because we simply calculated all of the factorials that came under it. So here's a well-known example of recursion, the Fibonacci numbers. And I just want to quickly cover what exactly the Fibonacci numbers, what they are in the first place before we actually use them in some examples. So these are some examples of the Fibonacci numbers. And to put it simply, the Fibonacci numbers are just for any element. So we can index them as at 0, like every other, like imagine it as an array. So to calculate the nth Fibonacci number, we just need to know what the two numbers before it were. So for example, this is the 0th Fibonacci number and the first Fibonacci number. These two are our base cases. So as long as we know these, we can calculate any Fibonacci number. So if I want the 5th Fibonacci number, for example, I can just look here and say 2 plus 1, the last two numbers, add them together, and I will get 3. And it's the same thing here. 5 is equal to 3 plus 2. 8 is equal to 5 plus 3. You just basically add the two numbers that came before it. So what is our recursive definition for this? Well, it looks exactly like this. So for our base cases, we know that for n equals 1, our Fibonacci number is just 0, and for n equals 2, our Fibonacci number is just 1. And then as long as we have those base cases, we can sum up the last two Fibonacci numbers to get our current Fibonacci number. So this is exactly what's going on here. These are our base cases, and we say the current Fibonacci is equal to the one before it and the 2 that came before. So in this case, we have Fibonacci of 5, which is 0, plus 1, which is our base cases, give us 1. 1 plus 1 gives us 2. 2 plus 1 gives us 3, and so on and so forth. And then eventually we get to 5 because 3 plus 2 is equal to 5. So what does the recursion tree look like for the Fibonacci numbers? So here's a little bit of a demo. There is a very nice website for visualizations. It's called visualgo.net. And if I want to visualize a recursion tree, you could just go over here. And I find this website very useful in creating these recursive trees for either very common recursive functions or functions that you write yourself. So if you go down here, you'll see that there's a little drop-down menu of all of the very common recursive problems. And so the one that we'll be doing today is Fibonacci numbers. And then of course you can write your own code in here if you want to see what the recursion tree looks like for your recursive function. But for example, we can start off with factorial numbers just to show you what the website looks like. So here, if I want to find factorial of 4, we know that the recursion tree is just essentially a straight line. So we start by we start at 4. 4 needs the factorial of 3 to compute. 3 needs the factorial of 2 to compute. And 2 needs the factorial of 1 to compute. This is the same recursive tree that we saw in the slides, but I just want to show you how the website works. So the return value is here, 1, 2, factorial of 3 is 6, and factorial of 4 is 24. So this is how the website works. So now, if we want to see what the factorial, or rather what the Fibonacci function looks like in a recursive tree, we can see that Fibonacci of 5 will obviously start at 5, and Fibonacci of 5 needs to call Fibonacci of 4. Because if you remember, when we looked at the code, in the order of how this code executes, we need to first find what Fibonacci of n minus 1 is before we move on to Fibonacci of n minus 2 in the execution order. So here, Fibonacci of 5 will go on to first compute Fibonacci of 4. Fibonacci of 4 will then go on to do the same exact thing. It will need Fibonacci of 3, which will need 2, which will need 1. So we basically go all the way down the recursive tree, and we only start propagating back up when we hit a base case. So our base case for the Fibonacci numbers, one of them is n equals 1. So here, since n is equal to 1, we return 1, and then we start propagating back up. And then since we said that the other thing that we needed to compute Fibonacci numbers is n minus 2, then we propagate up back to f of 2, and then go straight back down to get Fibonacci of n minus 2, which is 0. 0 will return 0, and then we propagate back up. So now f of 2 is now done. So then we propagate up even further, back up to 3. 3 will go back down so it can get Fibonacci of n minus 2, which is f of 1. That will return 1, and I'll just go ahead and let the rest of the visualization continue so you can see how this plays out. Basically what's going on is that you're able to build this recursive tree to visualize what's going on more in your code. We will go over the recursive tree a little bit more later on in the lecture, but for now I just thought that this website would be really useful in looking at how a recursive function actually executes. And so I'll just speed it up a little bit. Might as well. So it works all the way back up the tree, and we can see that Fibonacci of 5 is in fact equal to 5, just like how we saw it in the slides. So let's do a very quick set of Kahoot questions. The Kahoot questions won't be very difficult today. It's just going to be mainly for attendance. But here's the code. Join in. You guys have like 2 minutes. No extra credit for today's Kahoot because it's really simple. I hope everyone's in. We'll do like 20 more seconds. Alright, I'll get started. Yeah, no extra credit for today's Kahoot because the questions are pretty simple. Mainly for attendance. So the recursion tree for factorial function is just a straight line, true or false. Okay, so this is in fact true, and I can show you why very quickly if we just look back at the slides. So this was the recursive tree for the factorial function. We said that, factorial of n, every single time we compute factorial of n, we need to also compute factorial of n minus 1. Let's get the pointer here. Factorial of n minus 1. And so since we need that, every single time we call the function, we'll just keep on going downwards until we hit a base case, which is f of 1, as we see here. So the factorial function, the recursive tree, is just basically a straight line all the way down because we're only doing, one reduction at a time, factorial of n minus 1. We're not branching out into multiple function calls. So this is the recursion tree for the factorial function. It's just a straight line. So well done to the 16 of you. And we'll just do one more. The recursion tree for the Fibonacci implementation is just a straight line, true or false. Okay, so much better on this one. We have, for the Fibonacci function, we saw right over here, it is most certainly not a straight line because, as we said before, every call of Fibonacci needs both Fibonacci of n-1 and Fibonacci of n-2. So every single time we make that recursive call, it'll branch off into two function calls as long as it's not a base case. So here we have 5, it branches off into 4 and 3, which branches off into so on and so forth. So let's go ahead and get back into the question or the slides here. Okay, here we are. So that was basically all we were going to talk about with recursion trees, but we will go a little bit deeper in towards the end of the lecture. Here's another sort of visualization that you can have with recursion that I think will kind of help understand a little bit better what's going on under the hood, and that is the call stack. So if you remember from the Rust lectures all the way back in before spring break, we talked about how every single time we call a function, we create what is called a stack frame. And so you can think about this as a person just sitting down at a table that is reading your code line by line and writing down things on pieces of paper for every single function call. So we said, you know, for example, this code right here, we have a main function that just basically calls another function. So if you have a person that's sitting down at a table reading your code line by line, they'll start at main because that's where we start our programs. You know, they'll write the name of the function on the stack frame, the piece of paper, and then they'll write all the variables that you declared on it. And then we'll notice here we're calling another function. So when we call another function, we'll just put that piece of paper down, pull up a new piece of paper for our new function, write down the name of it, in this case is other function, write down the variables that are associated with it. Here we have other number is equal to 5. And then that's all that function does. It doesn't do anything more. It doesn't call any other functions. So we rip up that piece of paper and throw it away. And then we pick up back at the function that we were originally at, which is main. This after this function call, we're not doing anything else. So we just rip up the paper, throw it away, and that's the end of our program. So that's a little bit of an intuition behind these stack frames that we talked about a while back as a review. So let's see how this looks when it comes to recursive functions. So let's go back to the factorial example that we talked about earlier. So here is very similar code, except the main function is calling the factorial function with n equals 5. And inside of the factorial function, we have the same thing, the base case, and then, you know, we're reducing the size of the problem every single time. So the first thing that we do when we read a program is we start at main, of course. So we have a stack frame for main. And this is, of course, our stack. I simplified it a bit because the paper example would get too crazy. So these are our stack frames, and this is our stack. So we call, the first thing that we do is we call main, and then after that, we read in our factorial of 5 function call. So we put that stack frame on the stack. So we notice that f of 5 needs f of 4, similar to what we saw in the recursive tree. So then we will call that function again and put that on top of the call stack. So now we are in factorial of 4. And so the reason why we're using this call stack is because the state of f of 5 can't just be thrown away, right? We need to wait until f of 4 resolves before we can compute f of 5. So we put it on the call stack to basically say, once this is done, I'll just basically put the result into f of 5, and then I'll have my answer. But then we notice that f of 4 is reduced itself. We need to actually compute f of 4, which again needs f of 3. So we put that on top of the call stack. And we keep on doing this all the way until we hit a base case, similar to what we saw in the recursive tree. And the reason why we do this is, like we said, f of 5 needs f of 4, which needs f of 3, which needs 2, 1, and so on and so forth. But once we actually have a base case, then we can start propagating downwards. So here, f of 1 we know is a base case. We can just return 1. And so that function call will just simply return 1 and then pop off the stack because we don't need it anymore. And you can imagine this being like the person sitting on the table just ripping up the stack frame and throwing it away. All the memory associated with it is cleared. And so now we're at f of 2. So f of 2 we know is going to be 2 times f of 1. Well, since f of 1 returned 1, we know that it's just 2 times 1. So f of 2 will be popped off of the top of the call stack and return 2. And we keep on doing this. We'll have 3 times f of 2, which is just 6. So f of 3 will return 6 and pop it off of the top of the call stack. And we keep on doing this all the way until we go back to f of 5, which will then return 120 because we're able to use the value of the last function call, essentially. And so once f of 5 returns 120, then our main function is done because there's nothing that comes after that, and it's just popped off of the top of the call stack, and our program is over. So does anyone have any questions about the call stack before we continue? Because I'm going to show how it works with the Fibonacci numbers. So any questions before we continue? You guys are going crazy in the chat today. Let me just say that. You guys are some wild people. I'm assuming no questions, so we'll just keep on going. So we can see how the recursive call stack works with the factorial function, but now we can kind of build off of these concepts with the factorial function. So the factorial function, similar to how the recursion tree wasn't very simple, the call stack is a little bit different as well. So here is the same code that we saw earlier with the Fibonacci function. In our main, we're calling Fibonacci for n equals 5. And I just basically copied and pasted the same Fibonacci function that we saw earlier. So I'm going to actually, while showing you guys the call stack, also build the recursion tree right over here as we go through the problem. So we start off with f of 5. Or actually, sorry, we start off with the main function. So the program, our computer will call the main function. And then after that, we call Fibonacci of 5. So here's the start of our recursive tree, and we can see how this function will branch off into other function calls. So f of 5 goes to the top of the call stack, and our recursive tree, of course, f of 5 becomes the head, or the root rather. So now f of 5 needs both f of 4 and f of 3, because that's n minus 1 and n minus 2. But again, as we said earlier, since Fibonacci of n minus 1 in the code comes first, we have to execute Fibonacci of n minus 1 first. So f of 5 will call f of 4. F of 4 goes onto the top of the call stack, and we know that f of 4 is now running the same exact function all over again. And it's the same exact thing. Fibonacci of 4 needs to execute Fibonacci of n minus 1 before it does Fibonacci of n minus 2. So f of 4 will compute f of 3 now. F of 3 goes to the top of the call stack, and we keep on doing this until we hit a base case. So we know that f of 2 is in fact a base case because when n equals 2, we simply return 1. So now that we've hit this base case, we've propagated all the way down left in our tree. Now that we've hit this base case, in our recursive tree, we can start working back up. So f of 2 will return 1 like our function says, and then that stack frame, if you notice, is popped off of the top of the call stack because we don't need that function call anymore. So f of 3 is now able to use the result of f of 2, and since we have that, we can now compute Fibonacci of n minus 2 because this function call on the left has resolved. So what is Fibonacci of n minus 2? Well, that will be 3 minus 2, which is 1. Fibonacci of 1 is one of our base cases, so we return 0. And notice that that function call was added to the top of the call stack. So f of 1 will return 0, we return 0, pop it off the top of the call stack, and now f of 3 is able to say 1 plus 0, because that's n minus 1 plus n minus 2. So f of 3 will then resolve itself, which is, it will just return 1, of course. So that function is popped off of the top of the call stack, and now we go upwards. Now we're at f of 4. So it's the same thing with all of the other function calls. F of 4 has finished computing n minus 1. We know that n minus 1 is 1, like we saw here. And now we can actually start continuing and calculating Fibonacci of n minus 2. So Fibonacci of n minus 2 is 4 minus 2. So we do f of 2. What is f of 2? Well, it's a base case, so now we can just return 1 and pop it off of the top of our call stack. So what is Fibonacci of 4? Well, it's Fibonacci of n minus 1 plus n minus 2, which is just in this case 2. So f of 4 returns 2, and we propagate further up and pop it off of the top of our call stack. So now we're all the way back up to Fibonacci of 5. This is what we were trying to compute in the first place. And the reason why we went down to the left of the tree is because, again, we had to compute this first. So now we can start working down to the right of the tree, which is Fibonacci of n minus 2. So 5 minus 2 is 3, so we want to calculate f of 3. We put that function on the top of the call stack, just like any other function, and now we do what we've been doing the entire time. We keep going down all the way until we hit a base case. So f of 3 will break down into f of 2. f of 2 is a base case. It'll return 1 and pop it off the top of the call stack. It will call f of 1, which is on the top of the call stack. It'll return 0. And by now, I hope it's coming into the big picture. F of 3 returns 1. And now finally, we can give you the value of Fibonacci of 5. So Fibonacci of 5 is equal to 2 plus 1. And we know that the fifth Fibonacci number is 3, because we can just sum those two together, pop it off the top of the call stack, it returns. Main is done after this function call because there's nothing that comes after it. So it's off the call stack, and we celebrate. We've figured out what Fibonacci of 5 is. And that's, of course, how it is with any other function call to this function. So I think it just helps to kind of visualize what's going on when you call a recursive function, how that recursive function will break off into its own recursive calls, into its own function calls, and how the state of those functions is saved on the call stack. But since the state of those functions is saved, you have to notice that this call stack actually takes up memory because we're saving state in our computer. So since this actually takes up memory, we have to kind of realize something here. This is why missing a base case in our code is so fatal. So we can see this example here. Let's say we try to write an implementation of factorial of n, and we just forgot to include our base case. This is actually a lot more common than you think. Factorial function, of course, is fairly trivial, but when it comes to more complex recursive functions where the base cases aren't always super clear, or you have, 3, 4 base cases, it's, somewhat common to actually forget what one of the base cases are when you actually go to write it, and you end up running your code, and things go wrong. Well, why do they go wrong? Well, like we said, the call stack takes up memory in our computer. So what happens when we try to run factorial of 5 with this factorial function that forgot to write a base case? Well, factorial of 5 needs factorial of 4, which is n minus 1, which needs 3, which needs 2, which needs 1, which needs 0, which needs -1, -2, -3, -4, and it'll keep on going infinitely until your whole computer explodes and you start crying. So this is why it is super important to get your base cases correct. And so if you noticed what happened here, our stack literally overflowed until we ran out of memory in our computer. And so I hope the visual made this clear. This is a Stack Overflow. A lot of people actually don't know why the website is named Stack Overflow, or they don't know what a Stack Overflow error is. This is exactly it. It's what happens when our recursion either goes infinitely or goes too deep. Because there are some cases where the size of our problem is really large, and recursion might actually just simply run out of memory, because if you remember when we were building that recursive tree, we had to go fairly deep before we were actually able to propagate upwards. The recursive trees for, Factorial or Fibonacci were actually quite small. We didn't actually have to, go more than like 5 levels of a recursion tree. And of course, the size of this call stack is drawn to Google Slides, but the recursive call stack is obviously much larger than this in our actual computer. I just wanted to, fit it all on the same slide. But this is what happens when we either forget to write a base case or the size of our problem requires more memory to actually execute when we use recursion. And so again, the call stack takes up memory, so this is actually one of the reasons to why recursion can also be inefficient. If you run certain functions iteratively, you'll notice that you're not really taking up any extra space unless you declare an array or you declare a hash map or whatever it is, right? You declare variables, stuff like that. That takes up space. But you don't actually need these stack frames unless you call other functions inside of, let's say, your for loop. But recursion, on the other hand, since it needs to save the state of these function calls, it can take up a lot of memory. And so there are some implementations that actually might be done better iteratively rather than recursively, because there are some times where recursion can actually take up more space than you need, and as a result, it can be fairly inefficient. However, another thing that we need to consider is that there are some cases where recursion actually is a bit more readable. It is a bit, cleaner to write. Sometimes the iterative version of a recursive function is quite messy. Anything that you write recursively can be written iteratively as well. It's not like there's some sort of, block between what you can write in one versus the other. But there are trade-offs between the two types of writing, your algorithms. And these are trade-offs that you want to keep in mind. So don't always write recursion just because it seems really cool. This is something that Jeff mentions a lot in CS125, but there are actual trade-offs that you need to keep in mind. So with that, we'll do a quick Kahoot question. I believe our final one. Questions aren't very difficult today. So the question is, recursion is always the best way to implement something, true or false? I hope it's clear by now. Okay, so well done to the 22 of you. Yeah, recursion is not always the best way to implement something. That's basically what I talked about right now. You will get better at writing recursive functions as you practice them more, but I hope that the visualizations that we showed today were a bit more helpful in understanding what's actually going on under the hood and kind of demystifying, the recursion magic behind like these algorithms and when you actually write them in your code yourself. We will continue our recursive strategies on Thursday. Rohan will do that lecture, and we'll go a little bit more in detail about how there are some cases where recursion is actually quite good, and there are some cases where recursion is quite inefficient. Today we talked about how the memory side of things can be inefficient, but on Thursday we'll talk about time complexity rather than space complexity. But for today, a little bit of a shorter lecture. You guys are good to call it here.